Have you ever played the game 2048? It's one of those classic games that tricks you into critical thinking, including math, pattern recognition, and problem solving. If you have not, then I highly recommend you try it out for free by going to the top link in the description. It might help you understand the rules better. What if we could manipulate this classic game to reveal the secrets of one of math's greatest unsolved problems? In case you did not follow my advice to play a bit of 2048, then allow me to explain the rules quickly. At the start of this game, you have a 4x4 grid with 2 tiles. The goal of the game is to add these tiles together to eventually reach the goal of the grid containing a tile with the value of 2048. Each time the player makes a move, a new tile with the value of 2 is added to the grid. A move is defined as any movement of a tile. Tiles will move in the direction of the player's choosing until they hit the grid wall or another tile against the wall. If the colliding tiles have the same value, they are added together. For this, we are going to ignore the losing condition and assume that there will always be room for movement and room to add new tiles. Now, for this example, we are going to take this base idea and modify it slightly. The first change to the base game. When the game starts, the player can choose their own tiles. They can choose any number of tiles with any value within them. So, for our example, let's use this layout. You may notice that any tile in this grid can be rewritten as a power of 2, so let's do that. The same principles still apply, but now the tiles must have matching powers. When these tiles are added together, they create a single tile with 1 power higher. For example, if we add 2 4 tiles together, we get 8. And similarly, if we add 2 2 to the power of 2 tiles together, we get 2 to the power of 3, which is 8. This change is simple enough and does not change the basic idea of the game. The second change that we are going to make is that we will lower the minimum value of a tile to 1, or in our version, 2 to the power of 0. Again, this change does not massively alter the game, it only increases the number of moves you need to make to reach the final goal. The third change is where we start to alter the rules ever so slightly. And for this, we will redefine what qualifies as the end of a move. The same principle will apply, where a move is considered completed when all tiles have stopped moving. However, a move is only considered complete once there are no more possible merges, that is, no duplicate powers left. In other words, the player is allowed to move the tiles as many times as they need to remove all duplicate tiles. The player is also allowed to move tiles individually instead of all blocks moving together. For argument's sake, we will then consider tiles as moving if their value can still change, thus the move is still incomplete. The second condition of a move being complete is that there must be a tile with the value of 1 or 2 to the power of 0 contained in the grid. This is achieved by taking the tile with the lowest power and subtracting that power from all the tiles in the grid, including itself. So, for this example, we have these tiles left after all duplicates were removed. We subtract 2 from each power and now we have these remaining tiles. The move is now considered to be complete. With the move now complete, we must add new tiles. In the original, we added a tile with the lowest value, that being 2. In this version of the game, we will add multiple tiles. The tiles that are added are duplicates of the existing tiles but 1 power higher, as well as a tile with the lowest value, which is 1 or 2 to the power of 0. So, using the same example as before, we will now have a grid with the following tiles, our prior tiles and our new tiles. From this point, the game continues until, curiously, we are eventually left with a single 2 to the power of 0 tile. And after this point, every time at the end of a move, we will have that single 2 to the power of 0 tile. This is the Collatz conjecture, otherwise known as 3x plus 1, except viewed from a different perspective. The idea of this conjecture is that you can take any positive integer. If that number is odd, you multiply by 3 and add 1. If the number is even, you divide it by 2. If you continuously apply these 2 rules to your number and the results, the conjecture predicts that regardless of your starting number, you will reach 1, which will then loop into a 4 to 1 loop infinitely. While simple to test, there has been no way to prove with 100% certainty that this will be the fate of any positive integer. Numbers so large that I can't put them into perspective have been tested, and yet all of them fall into this loop. And it may seem silly to some of you. We are certain that this conjecture is correct, yet we refuse to outright say that it is correct. At the end of the day, there are an infinite number of numbers. There will always be more to test, and it only takes a single integer that does not conform to this conjecture to disprove it. But back to the topic at hand. Why 2048? Well, this version of the game is an easy way to visualize the problem and allows us to see certain patterns. For example, we know that 2 to the power 0 is the final step, or the goal. But using this visualization, we can see that as soon as we reach a single 2 to the power of n tile, it will collapse into this loop. So now we have the start of a collapsing funnel. We can then expand this funnel. The move right before we find a single 2 to the power of n tile will always end with any amount of tiles where the tiles are separated by 2 powers, as you can see here. So now we know that any combination of tiles that follows this pattern will eventually collapse. And we can continue expanding this funnel, and according to the conjecture, this funnel will expand infinitely to include all numbers. Writing the grid as the sum of the tiles and then continuing the game, we can also visualize why this conjecture will work for any positive integer. I know I take a risk in saying something so definitive, but take a look at the movement of the conjecture. The only term that is guaranteed to duplicate is 2 to the power 0. All other terms have no guarantee that they will produce duplicates and grow. Thus, it is impossible for the leading end of the expression to outgrow the trailing end. It is guaranteed that the trailing end will eventually catch up to the leading end by virtue of always producing at least one duplicate. This video is not intended as a proof of the Collatz conjecture. Instead, it serves as a new creative perspective of the problem. And ultimately, it acts as a justification for the sleep deprivation that this problem has caused me. Restructuring problems in ways that are more easily consumed is essential to understanding the problem itself and may eventually lead to something even greater. While I would highly discourage you from taking on this endless problem yourself, perhaps this video inspires you to approach a problem with a mathematical or in your life from a different perspective. If you enjoyed this video or you are otherwise infuriated by the lack of conclusion, I suggest you check out my main channel, where I delve into more unresolved mysteries in long-form documentaries. Thank you for watching.